Okay, 2013 Mechanics Level 3, question 1. So we've got a ball that's been tossed as a hollow ball with a mass of 0.310 kilograms, radius 0.0340 meters. Ball's thrown vertically upwards from rest. It rises through a height of 1.40 meters, then drops down again when it's released. It's moving upwards at 5.24 meters per second and rotating at 2.70 revolutions per second. During the throwing action, a tangential force of 0.480 newtons is applied to the surface of the ball for a period of 0.250 seconds. So we would presume a force is applied, something like that from the hand there. Show that the angular speed of the ball when it's released is 17 radians per second. This is just pretty straightforward. Omega equals 2 pi f. You've got the frequency given to you, 2.70 revolutions per second. 2 is 2, pi is pi. Plug it in and you should get that. It's a show question, so you have to actually do the calculation. You can't just write the answer. B, show that the average angular acceleration of the ball before it's released is 67.9 radians per second. Again, pretty straightforward, except this time the trick is the rotational notation. So angular acceleration is the change in angular velocity over the change in time. We're given the time there, and we're given the change because it starts from rest. So it equals that 17, which we're going to substitute into there. The change in omega is 17. Going on down, calculate the rotational inertia of the ball. This one's got a couple of steps in it, but again is relatively straightforward if you understand those rotational concepts. So we've got this equation, torque equals I alpha, Newton's second law in rotational form, which would be F equals ma. We've worked out A, and we can work out the torque from the force applied times the perpendicular distance. So if we can quickly cruise back up to the top there, we can see we were given the force of 0.480 newtons, and it's applied obviously at the radius, which we've got the radius there, so there's our force times our distance as the radius, and we can plug that in, rearrange for I, so we end up with a rotational inertia equals Fd over angular acceleration that was previously shown above. Okay, we're blazing through this one. I'm trying to keep it short. D, for the following two situations, explain whether the height to which the ball rises will be less than, greater than, or the same as the 1.40 meters from the original one. Ignore the effects of air resistance. That's nice. Part 1, the ball is not rotating but is given the same linear speed when it is released. Okay, this one seems kind of obvious, and it really is. It does reach the same height. I guess if it's given the same linear speed, we've got to look at our kinetic energy that it starts off with, and all of that kinetic energy will be converted to gravitational potential energy. So it's not rotating. That doesn't make any difference whether it's rotating or not, because if it's rotating, it'll have a constant angular velocity, whether it's zero or whether it's non-zero. Gravity is acting downwards in this linear sense, affecting that linear speed, and as gravity does work on the ball, you get energy stored as potential energy. And so when the kinetic energy is zero, the gravitational potential energy is maximum, and it's just going to be the same height as long as it has that same linear speed, because the rotational velocity, once again, has nothing to do with the... Good morning. Cool. Just a student arriving. Part 2, the ball is solid instead of hollow, but it has the same mass and radius. Okay, the amount of total work done to give the ball its linear and rotational, well, the same amount of total work is done to give it its rotational motion, and it has the same angular speed. So the only difference in this case is the total work. If we, I'm using the wrong tool, the total work is going to be the same. And remember, work is the energy converted. So if you are giving a solid ball, okay, but the same mass, solid ball, same mass and radius, that's going to have a lower rotational inertia, which means it'll take less energy to give it the same angular velocity. So there we go, same angular speed as we saw in there. If it's got the same angular speed, but it's taken less energy to get it to that speed, that means you've got more linear kinetic energy. More linear kinetic energy means more converted to gravitational potential energy. So that means it'll go higher. And there you have it. Is there another question? That's it.